Hello and welcome to part 3 of solving trig equations. In our last video we ended here where we practiced solving trig equations that have a quadratic form. Our first step was to substitute our sine function for a, just so that it's a little bit easier to see the quadratic form. So I had 2a squared plus 3a plus 1 is equal to 0, and then we factored and solved. What I'd like for you to do now is take a moment to pause the video and try example 648 on your own. So similarly, I am going to let a be sine of t so that I can substitute and see my quadratic form a little bit easier. So instead of sine of t, I have sine squared, which means a squared, minus 5 times sine of t, which is a, plus 3 is equal to 0. And then I factor. My method to factoring is to factor by grouping. So I multiply the first and last coefficients to get 6, and I want the two factors of positive 6 that add to a negative 5. So I'm going to be looking for two negative numbers, and those numbers would be negative 2 and negative 3. So then I rewrite my negative 5a as minus 2a minus 3a. I just got those numbers here on the right. So 2a squared minus 2a minus 3a plus 3 is equal to 0. Factoring by grouping, I factor out a 2a from the left, and I'm left with a minus 1. I factor out a negative 3 from the right, and I'm left with an a minus 1. Then I see that a minus 1 is a repeated factor, so factoring that out, I've got a minus 1 times 2a minus 3 is equal to 0, which means that a minus 1 is equal to 0, or 2a minus 3 is equal to 0. So a is equal to 1, or a is equal to 3 halves. So now I found a, but a wasn't even in the question, so I need to go back and resubstitute the sine of t for a. So the sine of t is 1, and the sine of t is 3 over 2. So I am looking for the sine value on the interval from 0 to 2 pi, where my sine value is 1. And that occurs where t is pi over 2. So t could equal pi over 2. Now my second equation, sine of t is 3 over 2, this is not going to give us a solution because our sine function is bounded between negative 1 and 1. This 3 over 2 is 1.5, which means that there is no sine value that will give us a 1.5, no angle that will give us a sine value of 1.5. So this has no solution, meaning that the only solution to this equation is pi over 2. Since we are only looking at the value from 0 to 2 pi, we only have a single solution. In our next section, we're going to solve trig equations using fundamental identities. In the equation I'm asked to solve, I see both a sine and a cosine function. In order to solve, I want to be able to isolate the trig function if possible. So what I'm going to do is I'm going to write one of these in terms of the other so that I have only one trig function. Ideally sine or cosine, but we can also write it in terms of tangent as well. Now looking at my equation, I've got 3 times the sine of t is equal to the square root of 3 times the cosine of t. I see that there is no addition or subtraction. I could write cosine in terms of sine or sine in terms of cosine and have either sine on both sides, or I can have cosine on both sides. But what I think is actually going to be easier is if I divide by cosine on both sides of my equation, then that allows me to have this in terms of tangent on the left-hand side. So I've got 3 times the tangent of t, because I know that sine over cosine is tangent, is equal to the square root of 3. I can then divide by 3 on both the left and the right-hand side of the equation, and I find that tangent of my angle is equal to the square root of 3 over 3. We are looking on the unit circle for where my tangent function is equal to square root 3 over 3 within the interval from 0 to 2 pi. So anywhere on the unit circle, I want tangent to be rad 3 over 3. So I'll go ahead and bring up my unit circle. And I know that tangent is sine over cosine, so I want my sine value to have a square root of 3, and my cosine value should not have a square root of 3. That's the method I'm going to start with to find the positive rad 3 over 3 for sine and cosine. So I'm going to go ahead and check out this angle of pi over 3 where my sine is square root 3 over 2 and my cosine is 1/2. And I'm also going to look at where both of them are negative because two negatives will divide to give me a positive. So I'm going to go ahead and look at 4 pi over 3 as well. So what I have found is that tangent of my angle pi over 3 is square root 3 over 2 over 1/2, which is when I multiply top and bottom by 2, I get square root of 3 over 1, which is not quite what I'm looking for. So that tells me that the angle that I chose with a sine of rad 3 over 2 and a cosine of 1/2 is not correct. So I'm going to go ahead and look for where my cosine has the square root of 3 and my sine has the 1/2. So I'm going to go ahead and instead of looking at my pi over 3, I'm going to look at pi over 6 with rad 3 over 2 and 1/2. And then I'll also look at where both of these values are negative, which would be at 7 pi over 6. So I'll go ahead and test these out. Tangent of pi over 6 is my sine is 1/2 over my cosine, which is square root 3 over 2, multiplying the numerator and denominator by 2's. In the numerator I get 1, and in the denominator I get square root of 3. So I have 1 over the square root of 3. And rationalizing, I do get square root of 3 over 3. So one of the angles that we are looking for to get a tangent of square root 3 over 3 is pi over 6. My second angle that I found, 7 pi over 6, is going to give us the same tangent value. And the reason that that is because I have exactly the same sine and cosine values, except they are both negative, which still simplifies to give us positive 1 over square root 3, which is positive square root 3 over 3. So on the interval from 0 to 2 pi, I found two angles that give me that tangent value of square root 3 over 3. And those values are t is pi over 6 or 7 pi over 6. Now we might be a little bit concerned about the fact that there are two other places where I have a sine of 1/2 and a cosine of square root 3 over 2. So you might see that relationship here. However, my cosine value is negative and my sine value is positive, which means that when I take the ratio of these two, I would in fact get a negative square root 3 over 3. But I'm looking for a positive square root 3 over 3, which is why I only have answers in the first and the third quadrants. Go ahead and take a moment to pause the video and try these next couple examples on your own. You will find it extremely helpful to use some of our identities, double angle and reduction identities, including the Pythagorean identities that I'm showing to you here, in order to solve the equations on our last slide. So go ahead and use these identities to help you solve the equations that are given here. My first step is to write everything in terms of one of my trig functions. So I'm going to take my sine squared function and rewrite it in terms of cosine. According to one of my Pythagorean identities, I know that sine squared plus cosine squared is equal to 1, which means that if I isolate just my cosine squared, that sine squared of theta is equal to 1 minus cosine squared of theta. So I can replace that sine squared with 1 minus cosine squared of theta is equal to 2 cosine of theta plus 2. Now the reason that I did this is so that I have everything now in terms of just cosine. So I'm going to move everything over to the right hand side since I see that this does take the form of a quadratic. So I'm going to want 0 on one side. So I have 0 is equal to, I'll put my positive cosine squared of theta first. Then I have a positive 2 times the cosine of theta plus 1. And then if I want, I can replace my cosine with an a to help me see the quadratic a little bit more clearly. So that would be cosine squared, so a squared plus 2 times cosine, which is 2 times a plus 1. And this factors into a plus 1 times a plus 1, or a plus 1 all squared, which means that a is equal to -1. So what we have found is that my cosine, I wrote this should be cosine squared, but in fact it should just be cosine of theta. So what we have found is that my cosine of theta is equal to -1. So inverse cosine of -1 gives us a theta value of pi. That is the only solution we are going to have on the interval from 0 to 2 pi. For example number 6, 4, 11, I'm going to go ahead and use one of my double angle identities, and I do want everything in terms of a single trig function, which would be sine. So I'm going to replace my cosine of 2 theta with 1 minus 2 sine squared theta. So this will be 1 minus 2 sine squared theta, or in this case we are talking about x, so sine squared x is equal to 3 sine of x plus 2. Now I have everything in terms of one trig function, and I do see that there is a quadratic here. So I'm going to go ahead and isolate my sine function by factoring. So I move everything over to the right so that I have 0 on the left. I have a positive 2 sine squared of x, a positive 3 sine of x, and then 2 minus 1 is a positive 1. Factoring, I can let a be equal to sine of x. So I've got 0 equals 2a squared plus 3 times a plus 1, which factors into 2a plus 1 and a plus 1. So then I find that a is equal to -1/2, or a is equal to -1. So my two values for sine then are -1/2, so sine of x is -1/2, or my sine of x could be a -1. On the interval from 0 to 2 pi, my sine value is -1 at 3 pi over 2. So my first solution for x is that x could be 3 pi over 2. Sine is -1/2 on the unit circle at the values of x being 7 pi over 6 and 11 pi over 6. So I have three solutions to my equation. X could be 3 pi over 2, x could be 7 pi over 6, or 11 pi over 6. That brings us to the end of our section. Thanks so much for watching our video and have a great day.